Hello, today I'll be doing Spec, and today I'll be doing proof by induction. And I have two questions. So the first one is not really on proof by induction, but it's about proving. And the second one will be more about proof by induction. First, the first question says, Goldbach's conjecture is that every even integer greater than 2 can be expressed as the sum of two primes. To date, no one has been able to prove this, although it has been verified for all integers less than 4 times 10 to the power of 18. So this is true, but we can't prove it. But so that means I can't prove it either. So yeah, so let's see Part A of this question wants us to express 100 and 112 as the sum of two prime numbers. So 100, right? 100 we can take out 11 and 89, and that would be prime numbers. Yeah. And for 112 we can just make the 11 into 13 plus 89. That's how it works. And for part B, we have to prove that 101 cannot be written as a sum of two prime numbers. It can't be written as a sum of two prime numbers. So 101 is odd, right? So odd is equal even plus odd. And then no prime numbers are even except 2. And 101 equals 2 plus 99. 99 is not prime, so the 1 can't be expressed as sum of two prime numbers. Yep, that should be fine. And for the next part, part C. Yep. Part C wants to express that 101 is a sum of three prime numbers. 101, right? So basically we can make that just equal. So we had 11. So we can use 7, 89. That is 96. 96. We still need 5. We can express like that. And for part D, it says assuming that Goldbach's conjecture is true, prove that every odd integer greater than 5 can be written as a sum of three prime numbers. So every odd integer integer greater than 5 I can write as I can basically just write that as 2x plus, if we plus 3, right, that makes 5, but 5 is not greater than 5, so the next odd number must be plus 5, and we want x to be a natural, not natural, I mean, yeah, natural, we want x to be a counting number, so 1, 2, 3, 4, 5, not 0, so yeah, and now 2x plus 5 can be written as 2x plus 2 plus 3. 2x plus 2 is every even number greater than 2. So according to Goldbach conjecture, 2x plus 2 should equal to prime 1, prime number 1 plus prime number 2. And so 2x plus 2 plus 3 equals prime 1 plus prime 2 plus 3. 3 is a prime. So that means every odd, let's just write 2x plus 5 equals prime 1 prime 2 prime. Not enough space. Plus prime prime 3. Every odd integer greater than 5 can be the sum of 3 prime numbers. That's it for this question. So can we go to the second question? This will be actually unproved by induction, like it includes it. So part 1 of this, it wants us to simplify 1 over n minus 1 minus 1 over n. So to simplify that, we just do 1 over n minus 1. Yes, oh my bad, that's n. And n minus 1, n minus 1. That just equals n minus 1, n minus n plus 1. That's simplified. And for part B, it asks us to hence show that 1 over 2 times 1 plus 1 over 3 times 2 plus 1 over 4 times 3 plus 1 over n minus 1 equals 1 take 1 over n. Okay, so basically each one, so basically 1 over 2 times 1 can just be written as this form according to part A. So write that as I might as well write, so 1 times 1 plus, right, 1 take 1 over 2, and like that. So we can write this as 1 over 2 take 1 over 3. So that means that we can continue this here. So that means this can just be rewritten as 1 take 1 over 2 plus 1 over 2 take 1 over 3 plus 1 over 3 take 1 over 4 plus that will be 1 and n minus 1 take n. So that should just equal to, because these will all cancel out like that, just leaves 1 take, because this will cancel out with the 1 in front, take 1 over n. and that equals the right hand side. So we can say that the left hand side equals, yeah. That's it for part B. And for part C, they want us to give another proof of the above equation using mathematical induction. So induction, I can say n equals 1. Not do 1, let's do 2, because 1's kind of weird, because you only go, like, you can't form a thing with 1. That just means 1 over 2 times 1. 1 take goes a half, and 1 take 1 over 2 equals a half. 1 half equals half. Proven. And now we want we want n to equal k. So how we're gonna do that? We're gonna do like 1 over 2 times 1 plus 3 times 2 plus 1 over 4 times 3 plus k minus 1 take 1 over k. Now we're going to do n equals k plus 1. So that should just equal to 1 take 1 plus 1, 3 times 2 3 plus, and we plus until 1 over k minus 1. So we want to add the next one, which is, it should be k, k, something, k, the thing's lagging, okay, k plus 1, k. Okay, and that whole thing should just, should just equal to this, because this whole part equals to this whole part. So we can just say that it is 1 take 1 over k plus 1 over k plus 1 k. And so we can say that this is just the left hand side equals this, right? So that means right hand side should equal to 1 take 1 over k plus 1. Let's see if that simplifies to that. So that becomes 1 take 1 over k plus 1 over k plus, okay, we can make that into 1 over k. Take 1 over k plus 1. So that should just equal 1 take 1 over k plus 1 and equals the right hand side. And we have proven that with induction, basically. And for part D, they want us to use the above equation, prove that 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over n squared is smaller than 2 for all n is counting numbers. And so how we'll do it is that 1 over k squared is definitely smaller than 1k minus 1k. Because this is bigger than the bottom, so it's inverse, so this will be smaller. So the bigger bottom will be smaller. And based off of that, we can say that 1 over 1 squared plus 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over n squared is smaller than this one. So okay, so that's that. Oh, wait. We'll have our first equation to be this, right? And our second equation to be 1 plus, because we don't have the 1 plus in the 1 to 2x 1 2 times 1 3 times 2 4 times 3 comes k plus n minus 1. Okay, so 2 should just equal to, because we added 1 on this side, it went from 1 take 1 over n to plus 1. So that just means 2 minus 1 over n. And because 1 is smaller than 2, as we got from here, each one smaller than each one, then that means 1 is smaller than 2 minus n. And n and as n is a counting number, where as a counting number, 1 is definitely smaller than 2, which means that we have proven that 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over n squared is smaller than 2 using the above equation. That's it, and that's proven. Yeah, that's it for today's questions and videos. All right, bye-bye.